Okay, let me see.
Welcome again, everyone, to the afternoon session. Our first speaker is David Radice. For those of you who don't know, David is an associate professor professor of physics at the Pennsylvania State University. His work includes compact binary mergers and core-collapse supernova. Today, he will speak about the current state of the Earth and future directions in understanding binary neutron star mergers. You can continue from that, David. Thank you very much.
Okay, thank you. Can you see my slides?
Yes, I can see your slides.
Okay, before I start, I just want to say that please feel free to interrupt me at any time during the talk. It's not really that important that I go through all the slides. I'm happy to have a discussion. And second, once again, I apologize for being late. So what I thought I would do today is give you some opinionated overview of what I think are important open problems in the field. But I will start with a bit of introduction. I don't think this audience probably needs a lot of introduction, but I want to emphasize a couple of points. The first is that the outcome of black hole neutron star mergers, as also double neutron star mergers, depends very sensitively on the properties of the binary, for example, the mass and the radius of the neutron star, or equivalently the mass and the equation of state, the mass of the spin of the black hole in the case of black hole neutron star mergers, and the dynamics of the merger, for example, whether or not the neutron star is disrupted outside of the ISCO in the case of black hole neutron star systems, is reflected in the counterpart and the multi-messenger signal from these events. So both the photon radiation that we see, the gravitational wave signal, as well as, say, the nucleosynthesis yields from these events. So what I think one of the key goals of numerical relativity is to map precisely this outcome. We have a good understanding of where things change from one regime to the other, where you go from, for example, plunge to the other disruption, but a lot of the details are still to be mapped. And the same thing happens in double neutron star systems. In this case, one of the key aspects of the dynamics that we are trying to probe, and that is reflected in all of the counterparts, is the time for black hole formation. If black hole formation occurs very rapidly, so we say prompt collapse, immediate at merger, then we can expect, especially for comparable mass ratio binaries, to have very electromagnetically dim or invisible binaries, while if black hole formation is delayed, we expect to have brighter electromagnetic counterparts. Again, this is more or less understood in terms of theory. However, the details, exactly where these different regimes take place, are still to be completely mapped with simulations. So these are some of the big open questions that the field is trying to address. These are only some of them. The nature of matter inside neutron stars, the problem of the production of heavy R process elements, whether or not neutron star mergers are the main contributor to the galactic chemical evolution of these elements is still something that is being actively debated. The connection between mergers and gamma ray burst, and possible application to cosmology, and of course, studying general relativity in the nonlinear regime. So I would start discussing electromagnetic counterparts, and I will focus on two types of counterparts. On the one hand, we have Kirnovi. These are the quasi-thermal counterpart produced by the radioactive decay of material that is ejected during merger, so shortly after the merger. There are different components of this ejecta. There is a component we call dynamic ejecta. This is material ejected promptly during merger by tidal torques or shocks. And there is a wind component that comes out at later times due to the evaporation of the disk around the remnant neutron star or black hole due to neutrino-driven winds and so on. The separation between dynamic and secular eject is somewhat artificial, but has to do with the fact that essentially our community is, for the most part, split in two. Most of the neutron star merger simulations are too short to really capture the secular ejecta. And a lot of the post-merger simulations start already from a disk around the compact object, so they don't include the dynamic ejecta. And we have really very few examples of a comprehensive simulation that spans both of these at the same time. On the other hand, we know that in order to explain the kilonova, we need to include all these different components, and we need to take into account the interaction between them. For example, this figure I took from this review by Masaru Shibata and Kento Tokezaka highlights the fact that the interaction between radiation emitted, say, by the secular ejecta, which is typically the most massive, and that is reprocessed by the dynamic ejecta that is more rapidly expanding, is necessary, is a necessary feature to be included in kilonova modeling. Now, in all of this, the dynamic merger plays a really important role. So to highlight this, I want to show, this is an old movie that we made of a binary neutron star merger. Here I cut everything above the orbital plane, so you can see the density color here in grams per cubic centimeter. And it's very slow down, so you will see really the dynamic of the merger. This is already the two stars about to merge. And you can see a little bit of the tidal tail coming through. At this point, what is happening is the stars are really merging. The core, so the two stars want to fuse, but they typically overshoot their equilibrium, and then there is a centrifugal bounce. This bounce generates a shock wave, and this shock wave is how most of the what we call dynamic ejecta is launched. Then over a time scale of 10 to 20 milliseconds, material is squished out from the collision interface between the stars. Essentially, it's the two cores of the stars want to merge together. They displace material that is hot, and ends up forming the accretion disk. So where the formation of black holes, of course, stops this process. If black holes are formed immediately upon merger, you have no shocks, you have essentially no disk unless the binary is very asymmetric, and in that case, you can have a disk just due to the tidal disruption of the secondary star. But in the case of comparable mass ratio binaries, essentially the amount of material left outside of the horizon is a direct function of the lifetime of the remnant. Not sure how well this played through Zoom. So here are some of the highlights. We have this dynamic ejecta tidal tail coming out. This is already in the late stage of the mergers. This is about 1 millisecond after merger, or half millisecond after the stars have come into contact. And again, this phase occurs either if you have larger symmetry in the binary, or if you can proceed to this phase before the formation of black holes. And then we have this shocked ejecta from the rebounds of the core, as you can see here. And at late times, we observe the formation of accretion disk. So I want to say a couple of things about the shocked ejecta, especially the very, very fast tail of the ejecta, since this is often explained in an overly simplified way. So this very fast component of the ejecta is the very tip of the ejecta, so we should care about this, even though it's a little bit of material in terms of mass. Is the screen that reprocesses most of the radiation we'll see at late times. And the very fast component of the ejecta, so here we took as very fast, being faster than 0.6 C, may also produce radiation due to the interaction between this ejecta and the interstellar medium. So it was long ago proposed by Nakar and Piran that this could give rise to a radio remnant, or equivalently, depending on the properties of the shock, this could also be seen in X-ray. It has not been seen yet. It was not observed for GW17 or H17. There were a couple of cases, a couple of moments in time where something that looked like this radio remnant or the X-ray component of this synchrotron shock was claimed to have been observed, but then subsequent observation kind of ruled out this hypothesis. So the nature of this fast expanding ejecta is, I think, illustrated, especially if you look at this plot in the upper right. where we have for one binary the central density in green, and then the outflow rate of this very fast ejecta in red. And we have time shifted the red outflow to take into account the time delay of propagation of the ejecta, because we measure the outflow at large distance from the center of the binary. So we took into account this time of flight of the ejecta. And what you can see is that this dynamic, very fast eject is not actually generated at the time the stars first come into contact, which is what often people claim. Instead, most of this ejecta is generated as a result of these bounces. So as the remnant rebounds, it launches the shockwave in the ejecta, and we have a peak in the outflow. And in this case, you can see two such peaks that correlates very strongly with these bounce sequences. And because it's the bounce of the ejecta that generates these outflows, they're actually primarily concentrated close to the orbital plane, as you can see in the figure in the middle, although they are almost nearly isotropic. It will be quite interesting if we are able to identify this super fast ejecta, because it will be kind of a direct evidence that the remnant was formed and bounced at least once before black hole formation. As I was mentioning, whether or not you have a disk left behind depends on two factors. In the case of comparable mass ratio binaries, the mass of the disk very strongly correlates with the lifetime of the remnant, and you can see this in this figure at the center. This is from one of our papers, but I think similar results have been reported by several other groups. So what we find, if you look at the solid lines for a moment, is that the mass of the disk increases with time after merger until a point, and that point is black hole formation, where part of the disk is actually immediately accreted if it finds itself within the ISCO. And in any case, the mass ejection from the remnant stops. If you have sufficiently large mass ratio, then you can tidally disrupt one of the two stars, and you have a massive disk. So whether or not you see a kilonova immediately tells you the following thing: either there was, if you see a kilonova, either there was no prompt collapse, or the mass ratio was sufficiently small in this case, or large, depending on whether you define it to be larger or smaller than 1. Of course, the mass ratio can be probed in principle with gravitational waves. So if we have high signal-to-noise ratio gravitational wave signals, and we see a kilonova, then we can exclude prompt collapse. And the idea that has been around for a while in the literature is that if we know whether or not a binary underwent prompt collapse, we can say something about the equation of state of neutron stars, because we immediately know something about this threshold mass from prompt collapse. And something that was pointed out by Andy Bauswine and others more than 10 years ago at this point is that the threshold mass above which you have prompt collapse is proportional to the maximum mass of a neutron star. And this makes sense because general relativity as a theory does not have a mass scale. So the only mass scale can be the mass scale that comes from the equation of state. And so the maximum mass for a non-rotating neutron star is the natural mass scale. And the proportionality constant, K threshold, which also depends on the equation of state. This proportionality constant has a roughly linear relation with the compactness of the maximum mass neutron star. So if we're able to say whether or not a binary underwent prompt collapse, and if we have a good theory measurement or theory estimates for what this K threshold should be, then we can say something about either M max or C max. So this is the idea that has been explored in many works. Maybe I will skip this in the interest of time. And similarly, if we can extend this to the unequal mass case, although we really need gravitational waves to confirm whether or not prompt collapse has occurred, interesting things happen. The first thing to notice here on the left, I plot the ratio, the threshold mass as a function of mass ratio to the threshold mass at equal mass for different equation of state. The first thing to notice is that if you change the mass ratio, even for extreme mass ratios for neutron stars, which is almost mass ratio 2, you have only less than a 10% correction to the threshold mass. However, what is interesting is that this 10% correction is not the same for all equations of state. There are two regimes, above mass ratio about 0.75, and for these comparable mass ratio systems, you don't have really significant tidal disruption. The threshold mass remains almost constant, is essentially constant within the error bars that we have in our simulations. And then it starts to change abruptly once you hit tidal disruption. The slope of this change, if we do a linear fit, correlates with properties of extreme matter. So this is in principle an interesting way to constrain the equation of state. In general, what we are trying to do, and not just my group, but the whole community, is to do something even more ambitious, which is multi-messenger inference. So our goal is to measure some parameters that here I call theta, given the data that we observe. This could be gravitational wave and electromagnetic data, and potentially other data too. And of course, we use Bayes' theorem to write this as a product of a prior on the parameters and the likelihood. And the key idea is to split the likelihood in gravitational wave part and electromagnetic part. There is a lot of work goes into how to model gravitational wave signal from binary neutron stars, including using numerical relativity. And you had talks about this in the workshop. So I will not really cover this. An area where numerical relativity has an important role to play and where I think more work is really needed is in modeling this electromagnetic likelihood. Here, the issue is that when you observe the kilonova, what we are really directly measuring are the properties of the ejecta and their composition, if we have spectra, for example, which are interesting things to measure, but not really the same parameters that we are measuring with gravitational wave observation. So if we want to do a joint inference, say, combine these different data streams to say something about the equation of state of the mass ratio of the binary, then we have to have a mapping between ejecta properties and simulation data that we can combine, for example, with a kilonova model to compute the likelihood. Now, the mapping, this is where a lot of work, I think, really needs to be done. For example, in this work in 2022, we did the follow-up simulations targeted to GW170817, and we measured ejected disk masses for all these binaries. And then we constructed fits to do a joint inference. However, in general, what we really want to be able to do is to have a model that predicts properties of the ejecta, given properties of the binary, properties of the disk, and so on. And as I will comment on in a moment, such models exist and have been proposed in the literature, but at least in some cases, the models that are out there at the moment are quite questionable, especially if you try to extrapolate them outside of the range of validity of the model, so where we don't have basically any simulations. These are some highlights, some results by different groups doing this kind of analysis. I chose two random ones. Well, actually, one is ours, but there are several other works, and I don't claim to have a comprehensive overview here, but this is kind of the general idea. So let me go back to the problem of fits and the properties of the ejecta from numerical relativity, because this is an area where I think a lot of work needs to be done with numerical relativity. Here I show, for the first part, fits on the dynamic ejecta for both double neutron stars and black hole neutron star system. The left one is the double neutron star system, and I show our results. So this is just the dynamic ejecta. The mass of the ejecta and the velocity of the ejecta as a function of the tidal parameter. So I show our results because the main claim I want to make is that these fits that are there for dynamic ejecta from double neutron star measure are completely unreliable. Actually, probably the best fit is just to take a constant value, the average of all possible simulations. We have fits in our paper, and we basically write, don't use these fits because they're not good, but this doesn't stop people from using them. And so I think this is very unsatisfactory what we have. For black hole neutron star system, the situation seems to be a little bit better because the physics of the dynamic ejecta, which is the physics of tidal disruption, is much better understood than the physics of shocks during mergers. And so here there are more reliable feeds and results. But again, also here, the coverage of parameter space is still somewhat limited. One problem with many of the feeds present in the literature is highlighted in this figure here. Here, what we show is ejecta mass and velocity, and ejecta mass and composition. The different colors are different numerical schemes, especially for the treatment of neutrinos. And you can see that all these schemes produce systematically different results. For example, if you don't include any neutrinos, piecewise polytropic equation of state systematically predict larger velocities than other models for the ejecta, and also tend to span a larger range of masses. And so be careful, because a lot of the models out there have been obtained by fitting essentially inconsistent data. And so there is a concern there. Unfortunately, the good, in quotes, simulation that include at least some treatment of neutrino radiation, which we now know is important, are very few, and they also come with large error bars. So the best we can do at the moment is try to come up with fits, but we need to take into account the fact that we are dealing with very heterogeneous data from numerical relativity, and there are systematic inconsistencies within the data. The case of the remnant disk from double neutron star mergers is a little bit more under control, and it's also a bit more under control for black hole neutron star mergers, because we understand much better what is the physics that govern the mass of the disk. In the case of low mass ratio binaries, so comparable mass ratio, the disk mass is basically just a function of the lifetime of the remnant, which you can map to the lambda twiddle, the tidal deformability of the binary. And for high mass ratios, the physics is the physics of tidal disruption, which we think we can capture in numerical relativity simulations. And something similar, of course, happens in black hole neutron star mergers, where everything is governed by the tidal disruption of the neutron star. Part of this disk is then ejected through a variety of processes. There are neutrino-driven winds. We have proposed the so-called spiral wave wind for disks around massive neutron stars, which we find a lot of the ejecta is actually powered by spiral waves that propagate in the disk and transport angular momentum, and that originate from non-axisymmetric deformation of the remnant before black hole formation. Another mechanism to eject material from these disks is through magnetized winds. A lot of works have explored this. Also recently, one problem with magnetized winds is that it's easy to make too much ejecta. For example, some of the simulations in the literature, like this work by Kent Takuchi, they start with very large magnetic field. They find very interesting results in terms of dynamo process and amplification of the field, but they also produce very large amount of ejecta, which would be inconsistent, for example, with GW170817. So we know that magnetized winds, if they play an important role in the ejecta, they cannot be as massive. So probably the magnetic field is not as strong or as well ordered as in some of these simulations. One aspect that is also emerging as an important open issue with these simulations is the fact that even when we include neutrino transport, we only take into account classical effects. We don't take into account the fact that neutrino can oscillate and change flavor. And what we found recently is that if we include the neutrino flavor transformation in some approximate way, we find that this can change, for example, the abundances of some elements by a factor of 5 or more, because electron type neutrinos are converted into mu and tau type neutrinos. And and so they don't interact as much with the ejecta. And for example, here, if we look at the figure at the bottom left, you will see different relative abundances for these different models. The blue model is a model where we didn't include neutrino mixing, so this is the baseline. While if we include neutrino mixing, we see significant enhancement in the production of the very heavy elements. Now, this enhancement is much larger than what we think our intrinsic error bars are for the neutrino transport. For example, if we compare our simulations with the simulations of François Foucault that does a neutrino transport in a completely different way, the differences are not at the level of factor 5. At the same time, so this shows that this effect is important. At the same time, we find that depending on how exactly we implement this neutrino mixing, which we're not doing in a self-consistent way, we are essentially doing ad hoc, we find that the results also change. So this is telling us that these effects are important and we need to do a much better job at including them. So summarizing what we discussed so far, what are some of the open issues with mass outflow and ejecta? Here we mentioned a few, understanding whether or not we can observe the fast ejecta, developing really precise mappings between binary properties and ejecta disk. This is something that's completely missing. A lot more work needs to be done exploring the parameter space, considering spins and so on. Understanding the nucleosynthesis from binaries, the role of neutrino flavor transformation, and so on. I know that since it started late, I'm probably running out of time now. So I want to say just a few things about the connection between mergers and gamma ray burst. Of course, in 2017, we famously saw a gamma ray burst 1.7 seconds after the merger. This we think was a jet that was slightly off axis, but was a regular short gamma ray burst. We don't expect this to be very common in the LIGO era because you really need to be lucky to have binaries either very close by so that you can see the jet off axis, or perfectly face on so that the jet is pointing towards us in order to see it. However, in the era of next generation detectors, for example, with Cosmic Explorer, we'll be able to see a lot more binaries and associated gamma ray burst. These are some of the questions we want to address. Understanding how these gamma ray bursts are powered, understanding whether all mergers power gamma ray bursts, whether they power only short or both short and long gamma ray bursts, and also hopefully to do joint constraints on the question of state by combining data from gravitational waves and gamma ray bursts. As I was mentioning, this will become increasingly relevant in the era of next generation detectors like Cosmic Explorer here in the US or Einstein Telescope in Europe. To give you an idea, Cosmic Explorer will see binary star mergers all the way to redshift 10. And so the peak of the mergers will be around probably redshift 2, which is where star formation peaked, or maybe slightly lower redshift. At those distances, we'll not be able to see the electromagnetic counterpart, the kilonova, but because we will see potentially hundreds of thousands of binaries per year, a large fraction will have a gamma ray burst pointed towards us. So the conjunction of gamma ray burst observation with gravitational waves will be very important in the 2030s, 2040s. I think I will skip this. Here we'll say a couple of things about the connection between post-merger gravitational wave gamma ray burst, showing a couple of speculative ideas that we have put out. One thing that we have recently started to look at, also in the context of next generation detectors, is the potential to see the gravitational wave signal from the black hole ring down that you can see here, for example, in purple. This is a prompt collapse event. Or in orange, this is a delayed collapse event at high frequency. It turns out that in some cases, this gravitational wave signal for binaries that are placed in the correct position in the sky and sufficiently close by may be detectable. This could be a rare event, maybe once every few years, but it will give us direct evidence of formation of black hole. And so this could be an important test for the theory. Another idea that we have recently proposed is to use modulation in the gamma reverse light curve also to probe the oscillation mode of the remnant. This is also speculative because we observed quasi-periodic oscillation in some gamma reversed, but we don't know their origin. So here in this work, we speculated that this quasi-periodic oscillation might be the result of this oscillation of the remnant. And we used the universal relation that have been developed in the context of gravitation wave astronomy to infer the equation of state from these events. Interestingly, if you take this at face value, this would give you some of the tightest constraint on the radius of neutron stars we have to date. Of course, this is somewhat speculative because we don't have a theory model that explains how these frequencies are imparted on the gamma ray light curve. And so this is something that we look forward to better understand and test also with next generation observatories. I think I will skip all of this since I arrived quite late. So here are some of the conclusions. We have learned a lot from the first few observations of neutron star mergers and chironovae. There is a lot more to learn. There are many open questions, and we need to develop a better theory. And for that, we need to have better simulation codes, better simulation technology. I know that the Einstein Toolkit is evolving and embracing, for example, GPU computing. In our group at Penn State, we are taking a different approach, and we are exploring the use of this new code called Athena K to also do numerical relativity. And if you're interested in learning about this code and perhaps comparing it or benchmarking it against the Einstein Toolkit, I want to advertise the fact we'll have a summer school at Penn State this year, and we'll have speakers like Manuela Campanelli, Jim Stone talk about computational astrophysics, and you'll be able to learn how this code works. Okay, with that, I think I will conclude. Thank you.
Thank you very much, David, for your talk and the perspective you shared. Now I will close I will turn off the recording and